Hello, my name is Sean Welchko, and today we will be talking about the wave nature of light. It just so turns out that we can describe much of the behavior of light as that of a wave. Maybe not quite like that. First, let's look at a couple of things that can also be described as waves. Ripples on a pond, perhaps sound waves. Now, while these are fine examples of waves, they do have a major difference between them and light. The waves I just described are what is known as physical waves. That is, that they need some sort of physical medium to travel through. In other words, the wave travels through stuff. Light is different. Light is an electromagnetic wave. This means that it is a series of perpendicular electric and magnetic fields propagating through space. To demonstrate the difference between physical and electromagnetic waves, let's try the following thought experiment. Let's say we pumped all the air out of this room. We would no longer have any medium for the physical waves to...
Don't worry, I'm okay. That was supposed to be a thought experiment. Here's a safety tip for anyone curious about the difference between physical waves and electromagnetic waves. Do not actually remove all the air from the room. It's generally bad for you. But back to the point that I was trying to make. If we did have an airless room, then the sound would have no medium to travel on. So you could no longer hear me, but since light is an electromagnetic wave and doesn't need a medium, you could still see me. Here is a typical depiction of an electromagnetic wave. We have the series of perpendicular electric and magnetic fields propagating through space. Being a wave, we can then use things like frequency and wavelength to describe them. This is probably not the first time that you've heard these terms. The visible light that we see, being an electromagnetic wave, is just a small section of what we call the electromagnetic spectrum. This spectrum contains wavelengths and frequencies ranging from the unimaginably tiny to the insanely huge. Although we can't see most of this spectrum, we experience many of these in our day-to-day and not-so-day-to-day lives. Things like the infrared beams we use to tell our televisions what to do, the UV rays that cause sunburns, microwaves that cook our food, radio waves that bring us our music, and X-rays that can see whether or not our bones are broken, as well as gamma rays that we can observe coming from the most massive explosions in our observable universe. While we may experience all these different forms of electromagnetic radiation in different ways, they all have one thing in common: the cosmic speed limit, the speed of light. Given the symbol of c, this speed is about 3 times 10 to the 8 meters per second, or 300 million meters per second, which is pretty fast, but is still finite. From all this, we can now use a wave speed equation to connect wavelength, frequency, and the speed of light. Now you can figure out just how big the radio waves broadcast by your favorite radio station really are. And that's pretty nifty stuff.
And so we now conclude our little discussion on the wave nature of light. To summarize, light is an electromagnetic wave and therefore does not need a physical medium to travel through. Light has a finite speed, and the light that we see is just a bit part of the much larger electromagnetic spectrum. Thanks for watching, and have a great day.
Ooh, credits. Exciting stuff. This is fun times. Yeah. Okay, I really need to get music or something in here.